Hi, hello everyone. I am Professor Vikranth Racherla. I am one of the class teachers for Mechanical Measurements and Mechatronics Laboratory. I am going to walk you through the steps that are involved in carrying out the experiment on weight measurement using load cell. Let's first start with the circuit diagram for this problem. So what we have is we have a bar type load cell. The load cell is fixed at one of the ends and the force is applied through the other end. This is a 5 kilogram or 5000 grams rated bar type load cell. The load cell has got 4 strain gauges attached to it. There are 2 strain gauges on the top and 2 on the bottom. The strain gauges are connected in this particular manner. So a full bridge Wheatstone circuit is being used. In here R denotes the resistance of the strain gauge. Here the resistance value is 1000 ohms. So there are 4 wires which are coming out of this particular load cell. E plus and E minus are used to energize the Wheatstone bridge. So in this particular experiment, 5 volts is being applied across E plus and E minus. Now the 2 strain gauges on the top, one of them will be here and another over here. The strain gauges on the bottom, one of them will be here, another will be here. So as we apply the load on the load cell, what happens is on the top the resistance of the strain gauges increases just by a little bit, and on the bottom it reduces just like by a little bit. Because of this, a voltage gets generated across A plus and A minus terminals, that is across the green and the white colored wires. The voltage generated is very small. It is of the order of fraction of a millivolt to a maximum of about 5 millivolt. Now the signal is weak, particularly in comparison to the noise which would get generated due to the electromagnetic field around us. So what we will require is, before we can analyze the signal, it will have to be filtered and amplified. So for that we make use of HX711 module. The HX711 module does 3 things. It filters the signal, it removes the 50 Hz noise which comes in from the AC current which is passing through wires all around us. Next, it amplifies the signal using a operational amplifier. It actually uses a programmable gain amplifier. Once the signal is amplified, then it is digitized using a 24-bit analog to digital converter or 24-bit ADC. All these 3 things, filtering, amplification and digitization, happen on this HX711 module. So the 4 wires of the load cell are connected across E plus, E minus, A plus and A minus pins of the HX711 module. Now once the signal is amplified and digitized, the information from the load cell is transmitted next to the microcontroller board. In this experiment, we make use of Arduino UNO R3 microcontroller board. This is one of the most popular microcontroller boards, particularly for beginners all across the world. The microcontroller board has been in use for more than 10 years now, and there are a very large number of applications that can be executed using this microcontroller board. So the data from the HX711 module is transmitted to Arduino UNO via I2C protocol. I2C stands for inter-integrated circuit protocol. In this protocol, you require 4 wires, VCC and ground to power the module, a clock wire to basically say in what is the time associated with transmission of a bit, and a data wire. So there is a oscillator circuit on the HX711 module which generates a clock signal, and then the data corresponding to the weight being measured from the load cell is transmitted via the data pin. Now the clock signal is connected to the digital input output pin number 5, and the data is connected to digital input output pin number 4. Now whatever information is received by the microcontroller board, it is shown on a LCD screen and it is also transmitted to a computer. So once again, to pass on the information to the LCD screen, we use I2C protocol, and in this particular case the clock signal is connected to the analog pin A5, and the data pin on the LCD module is connected to analog pin A4. We use a breadboard within this particular experiment in order to connect the wires appropriately. Whatever wires are shown over here in the experiment, you will be using jumper cables for connecting the microcontroller board to the LCD module and HX711 module. Now on the breadboard, some simple points to note is all the pins next to this plus sign or above the red colored line over here are shorted. So if I take this 5 volt output from the Arduino and connect it over here, then all the pins next to this red colored line will be at 5 volts. Similarly, if I attach a jumper cable to the ground pin on Arduino Uno and the pin next to this black colored line on the breadboard, then all the pins next to this black colored line would be at ground. It is important to note that all the devices in a particular experiment need to have a common ground. So it makes sense that we use a breadboard to basically ensure that all the devices are being powered with the same voltage and the same ground. In this case we are using 5 volts as the excitation voltage. Now the Arduino Uno board itself can be powered in 3 ways. It can be powered using a USB cable. The USB cable serves 2 purposes. It powers the Arduino Uno board, and we can also use the cable to upload the program onto the board, onto the bootloader. For uploading, we use UART serial communication. UART stands for Universal Asynchronous Receiver Transmitter. UART protocol stands for Universal Asynchronous Receiver Transmitter Protocol. Now, in addition to using USB to power Arduino Uno, you can also power it with a DC jack. We typically use 9 volt jacks to power the Arduino, or we can also power it using this VIN pin. Now the power pins for Arduino are over here, and as you can see, Arduino is capable of providing 3.3 volt output as well as 5 volt output with respect to the ground of the microcontroller board. Now whenever you power the Arduino, there is a green colored LED at the bottom over here that needs to turn on. That is your indicator that this indicates that the board is being powered. In case of a faulty USB cable, the light, the green LED will not glow. There are a couple of LEDs over here next to which TX and RX are written. TX for transmission and RX for receipt. So for example, when we are transmitting some data from Arduino to the computer, then the TX LED will glow, and when we are transmitting the program from the computer to the Arduino, then the RX pin will glow. Now with regards to the other pins, there are 6 analog pins. So you can receive an analog voltage from any sensor. The analog voltage can be anywhere between 0 to 5 volt. Again, this is with respect to the ground of the microcontroller board. The received analog signal is digitized using a 10-bit ADC. So there will be basically 1024 levels of voltage, and you get somewhere around 5 millivolt resolution in the measurement. And in addition to the analog pins, you have a bunch of digital input output pins from 0 to 13. Each of these digital input output pins can provide a maximum current of 20 milliamperes. So if you try to draw more than 20 milliamperes, then you would end up damaging the microcontroller board. The microcontroller board as a whole can handle a maximum of 500 milliamps of current. So it means the net power handled by the microcontroller board cannot exceed much more than 500 milliamperes. So so this is the system that we will be looking at. Now whenever we have any digital device which is being connected to a microcontroller board, so in this case HX711 and LCD modules are digital devices, whereas load cell is an analog sensor, because basically there is no digitization which is being done over here. So to interpret the data that is being sent to or being received from the digital device, appropriate drivers will have to be installed. So we will talk about the program in just a minute. So the first thing that you need to do in order to go ahead with the experiment is, so we first connect the different units: load cell, HX711, LCD module, breadboard and Arduino microcontroller board as per the circuit diagram being shown over here. So I have already done this. So here is the system which has been constructed. So this is the Arduino Uno R3 board. This has been connected via the USB, this blue colored cable, to the CPU of the computer. And then you can see there is a green colored LED over here. Right next to it, on is written. So the board is already powered, and currently the board is transmitting information to the CPU. So next to the TX pin, a orange colored or yellow colored LED is glowing, and the microcontroller board via the HX711 module is connected to the load cell. The load cell is a bar type load cell. There is a hole in between. So when I apply a load over here, you can see the weight value is changing. When I apply the load, what happens is the strain gauges on the top, they stretch, and the strain gauges at the bottom, they compress, and this change in resistances through the Wheatstone bridge, basically this can be measured by measuring the voltages across A plus and A minus terminals. So the signal from the load cell is filtered, amplified, digitized on the HX711 module. This information is communicated to the microcontroller board, and then it is next in turn displayed over here. There is some tare weight error. So there is a button next to the USB cable. So if I just press this, I have pressed it now, there is a push button. So the program on the Arduino is being restarted, and after I restart the program, the weight needs to come to 0. So yeah, so I guess there is a small amount of hysteresis in the load cell that is there, because of which the weight doesn't go to 0, but it's slowly changing. Now next let us see as to how to develop the program to basically write onto this Arduino and do the measurement using the load cell. So for this, please first download Arduino IDE. So for that you may just go to Google, or directly in the browser you can say Arduino IDE, standing for Integrated Development Environment, download. So you can directly go to download and install Arduino IDE, and depending on your operating system, Windows, Mac or Linux, download the appropriate installation file and run it in order to install IDE. So once it has been installed, you can go to the search bar and type Arduino IDE and open the application. Okay. Now once the Arduino IDE is opened, you can go to File, Examples, HX711 ADC, Calibration, in order to calibrate the load cell which you have. I'll open this. Now this example comes with the library. So in order to use this particular, in order to execute this program, you will need to use some libraries. So there is a HX711 ADC library. So in order to install this library, what you have to do is you have to go to Tools, Manage Libraries. We will be using two libraries, HX711 and the LCD I2C. So for that, you first please type in the search menu HX711 underscore ADC. There is a library which has been created by Olav Calhout. So you please install that. I have already installed. Next, you please install liquid crystal underscore I2C. Okay, which has been written by Martin. Please install this library too. We will be requiring it a little later. So if you go through the code, so you may go to Manage Libraries. So this vanishes. Now before we go into execution of the program, there are a couple more things to be done. So first, let's go to Tools, Board. You have to select the appropriate board. So go to Board Manager, Arduino AVR boards, Arduino Uno. Next, we'll have to select the appropriate communication port, so that we would be able to the CPU would be able to communicate with Arduino Uno. So for that, go to Tools, Port, and select the appropriate port. So next to the relevant communication port, Arduino Uno will be written. So just select that. Now you can just first press on this verify button. So if everything is okay, then the program would compile. Now before we upload the program, let's just take a quick look at what this program does. So we first import the libraries corresponding to HX711 ADC. So this will help us read the data from the HX711 module. Then there is a EEP ROM. So this is the ROM, random access memory, on the Arduino board, which does not get erased even when the Arduino is powered off. So aspects related to calibration of the load cell and the calibration factor are written onto this EEP ROM. Now as far as this HX711 module is concerned, we are using the digital pin 4 for the data and digital pin 5 for the clock. Next, fine, so we create a HX711 constructor. And we define the address for this calibration factor, means for this EEP ROM. So EEP ROM address is being defined as 0. Then whenever we communicate, meaning when the program is being written from the CPU to the Arduino Uno board with UART communication protocol, the baud rate will have to be set. So we are saying that we will be transmitting 57,600 bits per second. So whenever you have something like serial.println, then on the serial monitor on the on the computer, you would be able to read this text. So when we execute this program, the first text you will read is starting, and then we are using some 2 seconds of stabilization time. In Arduino IDE, whenever we talk about time, this is time in milliseconds. So 2000 means 2 seconds. So if okay, and initially we will not keep any weight on the load cell, and we will set that as the tare weight condition, meaning 0 weight condition. If something is wrong, then the error message is printed. Otherwise, we will print setup is complete. Once setup is complete, we call something called the calibrate function. Now, whenever you run a program in Arduino, we create files with .ino extension, and these files have 2 functions, void setup and void loop. So the void setup function, it runs only once, and void loop function, it runs continuously. So this calibrate function, when it is called, it will say start calibration, and then it will say place the load cell. It will basically print all of this information. Println means after this text is printed on the serial monitor, the cursor will move to the next line. Now once all of this information is printed, it is asking us to type T from the serial monitor to mention that tare weight condition is being satisfied at that particular time. Then after that, it will ask us to place a known mass on the load cell. So this weight will be in grams. So once we place a known mass and then place its weight, then it will generate a calibration factor. And once it generates the calibration factor, it will ask us whether we want to save it to EEP ROM, in which case we don't have to write it down somewhere and then call it and all of that. It will stay in the EEP ROM, and then we can retrieve it whenever we want. So that's pretty much it really, and then we can continue calibrating it any number of times we want. So let me just press the upload command. So okay, now what I'm going to do is I'll minimize this screen. And then I will open this camera so that you can see what's going on. I'll put it over here. Alright, okay. Now let me press upload. Once I press upload, you will see that the weight over here disappears. So it is compiling the sketch and then uploading it onto the device. So once it has uploaded it, alright, it has uploaded it. Sorry, we are not dealing with the LCD screen during the calibration point. Now, in order to communicate with the Arduino code, we will be using the serial monitor. So I'll press on this serial monitor icon, which is there on the top right hand corner. So the program is starting, startup is completed. It is now saying send T from serial monitor to set up the tare offset. As you can see, currently there is no force which is applied on the surface of this particular load cell. So I will type T over here for tare weight and press enter. So then it is saying place a known mass on the load cell. So I am going to place a stapler which I know is 140.42 grams. I have used a precision balance in order to verify the weight. So what I will do is I will enter 140.42 gram and enter. So once I enter the known mass, then it has computed some calibration factor 435.39, and then it is asking me whether this is to be saved to EEPROM or not. I will say yes, enter. Then it is basically displaying the weight. So if I remove this, it has come to 0, means roughly 0. I'll place it back again, 140.6. So you can see about 0.2 grams error is there. It's coming back to 0. I can do this any number of times. So you can look at the repeatability of the system through this. Alright? Fine. So one thing to note about load cells is, typically load cells give you about 0.01% accuracy. So for a 5000 gram load cell, so in the load cell that we are working with, this load cell has a rating of 5000 grams. So 0.01% of 5000 grams is 0.5 grams. So 0.5 grams error is acceptable for this load cell. So currently we are getting about 0.2 grams of error. 0.2 grams of error. We can even check the resolution of this particular thing. So this is quite sensitive. So if I take a piece of paper, alright, and then if I am going to just put this on top of this and then do this, so you can see I'll remove it, maybe 0.5, 140.5, and this has come to 140.4. So you can see this was about 0.1 gram of weight. Alright, so now the calibration is completed. So once the calibration is completed, what you next do is you go to the Moodle. You go to the Moodle page. Just a second. Where is Moodle? Yeah, here. Moodle. Open the course, and then go to this force measurement using bar type load cell. Open this Arduino code, download it, and then open it via your Arduino IDE. So let's say I have done that. So this calibration is completed. I'll close it. Now I'll open the main sketch. Now this main sketch does the communication with the, this one does the communication with the LCD module also. So currently LCD module is not operational. See, one interesting thing about Arduino is that right now for you it may appear as if it is not doing anything, because the weight is not changing on the LCD screen, and there is no serial monitor which is on or anything. But then you can see that the TX light is glowing, meaning it is transmitting the information. It is just that you are not seeing it. So to see the information, you can just go to either the serial monitor. It is starting now. Okay, the calibration code is running, so again it is saying okay, press T and all that. I don't want to do that. So let's go to this main code now. In the main code, I am also using this liquid crystal I2C library. This EEPROM and wire are already built, means are by default installed libraries when you install the Arduino IDE. So alright, so let us just run this particular code. It is the same as the calibration code. The only difference is, in addition to the serial monitor, we are also sending the information to the LCD screen. On the LCD screen, we are only displaying it, the weight information up to one digit after decimal. That's because the reading is stable only up to the first digit after decimal. So let's run this code. So I'm directly going to upload. You can always compile initially and then upload, but pressing the upload button also does the job for you. So now once I uploaded it, you can see this has refreshed and the weight has come to 0. So now I'm going to sort of make this bigger now. Now what we can do is we can place the weights now. So let's say I place this battery. I have measured it with a precision balance, and that time it showed 35.54 gram. Here it is showing 35, sorry, it was 35.54, it is showing 35.8, again a 0.25 gram error. I can place this battery whose precise weight is 45.64 gram. Here it is showing 46.1, so 0.5 gram error. This stapler is 140.42 gram, it is showing 140.9. So you can see that the error in all the cases is around 0.5 gram. That's because there is a 0 error. So in order to restart and set the tare as 0, I can press this restart button next to this USB cable. If I press restart, means the program restarts. So the dead weight is 0. Now if I place the stapler, you can see the weight is showing 140.4. Original is also 140.4. So that's it really. So you just if you make the means set the tare as 0. So I'll set the it's almost 0 only in any case. So this is 35.54. You can see that the weight is being measured pretty precisely. Okay, some 0.1 gram error, which is acceptable, which is well within the limits. So that's about it. Now just one more thing before we close. So see, when we are getting the data, we can either visualize it using this serial monitor. Okay, so you can see that right now it is under empty condition, so the weight is about 0.1. I can place this battery, and this is about 35.5 grams. Now if I want to see it as a plot, I can go to serial plotter. So you can see that the value is being plotted over here. Now the serial monitor and plotter are good if we want to just take a look at it, but if we want to record the data, then what you can do is you can install an application called Doclite. Now once you install the application, you may open the same. So let me first close it and then I'll open it. So I'll open Doclite. I am starting a blank project. The comport, I am double clicking on it. It is Arduino Uno is in comp3. I'll select that. Baud rate is 57,600. Data bits is 8. Stop bit is 1. I'll say OK. Then there is an option to log the data, meaning store it in a file. So I'm storing it on the desktop in a folder called loadcelldata.txt. It will overwrite if there is already an existing data. The data is in ASCII format. So the 8 bits are being mapped to a character in ASCII. So also yes. And then I can run it in order to start. So you can see now that the means communication is starting and I'm receiving the data. Now for every second it is printing out the data. Alright, so right now it is 0. Oh, okay, let me do one thing. I will start again because the battery was there before. Okay, so you can see this. So right now no weight is there and it's showing us somewhere around 0.1 gram. Now I am placing the weight. It's showing us 35.7. Please note the actual weight is 35.54. I'll take this off. Then I'll stop. So now using Doclite, we will be able to basically record this data. So if I want to precisely know the error or something, I can just copy this data. By the way, every second, so it is showing information second wise. It is receiving it from Arduino, and there are 1, 3, 6, 9, 11. So we are receiving 11 samples per second. So I'll just copy this, and then if I want a precise error, I'll go to a Google Sheet. I'll basically paste it. I'll use a split to text separator. I'll put a custom. I'll put this left bracket, enter. So I can just remove this. Let's look at average of this. This comes to this. So this is measured weight. Actual weight in this case is 35.54 grams. Error is absolute of this minus actual, and then if I look at percentage error, so this will be equal to this by 100, sorry, by 5000 into 100. 5000 is the full measurement. So you can see this is less than 0.01%. As I told you, 0.01% of error is an acceptable error when it comes to load cells. Alright, so we will stop over here. For the 3 known weights, please take 5 measurements each. You may use Doclite, and for each measurement you may stop and run so that the tare is set for each of the measurements, and yeah, get the actual error and percentage error for each of the 5 measurements. And you may play around with the baud rate and anything else. Do not change the circuit though. Yeah, that's about it. Thank you. Have fun.